After that, I will talk about the installed propeller noise, where the propeller, we have installed the propeller upstream of the wing, and I will show how we can use the theory of counter-rotating propeller to predict various interaction noise sources associated with the propeller wing configuration. And I will show how there is a balance between the rotor alone and the interaction noise sources, and how they change with respect to the change in blade number, tip speed, as well as the separation distance between the propeller and the wing. And in the last one bit, I will talk about the installed propeller noise, where we are talk about in the effect of realistic wing features like a wing sweep, lean, and offset on the wake interaction noise. And I will show like these wing features can be used to design a low noise configuration, low noise propeller wing configuration, and then followed by summary. The introduction. So we know that the global interest in regional aircraft and urban air mobility has been increased recently due to the emergence of electric and distributed propulsion system. And we are going towards a new regime where we are trying to focus more on urban air mobility or the regional aircrafts. And when you try to type future regional aircrafts in a Google, you can see a various novel or different configurations being explored by the aircraft manufacturer. And one of the common features you can see is the open propellers, and those are mounted very close to the wing. So it's very important to analyze the different source mechanism associated with this kind of propellers in isolated condition, or the propeller which are installed very close to the wing. So today I'm going to talk about more on then a propeller in isolated condition, as well as the propeller which is when it's installed very close to the wing, how the noise generation mechanism changes when you vary the tip speed and the blade numbers. So first of all, I will talk about the isolated propeller noise. As I mentioned, I will talk about the balance between the tones and the broadband noise over the range of blade number and tip speed. And this work we have recently published in one of our journal article in International Journal of Aeroacoustics, and also we have few results published in one of the AAA conference. So first of all, what I consider is like we consider it just a rotor which is rotating in an isolated condition, and it is moving with the uniform motion of let's say Mach number mx in an axial direction. So in that case, we have the two components of the sources. One is the tones, and this is typically due to the loading and thickness noise. And as we are considering like propeller which is rotating relatively at subsonic speed, so we consider only the uh, kind of loading and the thickness noise. So this source is a kind of discrete in nature and occurs at the blade passing frequencies. And to estimate the noise, we use Paris model. And the next one, we have the broadband noise, which is due to the scattering of turbulent boundary layer at the uh, trailing edge of the blade, and which is continuous over the frequency range. And for that, we use a Plandu's model to estimate the broadband noise. So to use these models, we need some of the aerodynamics inputs. Like for the tonal noise, we need the lift and drag coefficient, which is distributed along the radial location of the blade. So to estimate those lift and drag coefficient, we use the X foil to estimate those lift and drag coefficient at a particular defined thrust. And for the broadband noise calculations, we need a kind of boundary layer parameters at the trailing edge of the blade, and those parameters again we have extracted from the X foil. So I'll just quickly show how these two formulations have a bit of similarities with each other, and this will be very helpful to explain the overall behavior or the balance between the tone and the broadband noise sources. So if you look for the just the tonal noise source, obviously it has a source strength which is shown by the green terms, and it has the radiation term associated with it. And you can see that this is a discrete in nature. That means at a particular blade passing frequency, only a single mode has been excited, and overall contribution at that blade passing frequencies comes from the single mode. But if you try to look for the broadband noise, we have used the strip theory, which is like kind of uses a different strips along the blade span, and the overall spectral density will be the sum of the spectral density of the individual spans. But the major important thing over here is kind of broadband noise is a kind of stochastics in nature, where you can see that each broadband frequency there are contributions from the numerous modes, which is summed over minus infinity to infinity, which is called nu. But the how many modes which are contributing to an individual frequency depend on their radiation efficiency. So in conclusion, what we can say is that at tonal noise, the tonal noise occurs at the discrete blade passing frequency, and only a single mode contributes to the that tonal noise at particular blade passing frequency. But at the broadband noise, at a particular frequency, there are contributions from numerous modes which are being excited. So what are the general assumptions of our study? Like what we assume is like the propeller thrust is a sum of thrust produced by the finite section of the blades along the span. And we assume the media of the sound is assumed to be rest, which is one of the major assumption of our study. And we also consider the full non-compactness along the chord as well as along the span direction. And we assume there is no sweep and lean in the blade profiles. So to carry out the parametric study, we impose some constraints, like we assume that the propeller diameter is fixed, and we maintain the propeller thrust as well, but at the same time we varied the blade numbers and tip speed. And as we know that the thrust is a kind of function of blade number and tip speed, but while varying those blade number and tip speed to maintain the constant thrust, we just rescale the lift and drag coefficients by using XPoil, and I will explain you in a moment how we did that. We have produced one of the subroutine to convert which takes a kind of thrust and some of the input parameters, and it will give a kind of distribution of lift and drag coefficients along the span. So apart from that, we assume that the blade solidity remains the constant when you are doing our entire parametric study. So at a constant blade diameter, the condition of constant blade solidity leads to a kind of the product of blade number into chord to be a constant. That means when you are increasing the blade numbers, you have to reduce the chord accordingly to maintain the blade solidity. So we looked at one of the baseline configurations from the ATR 42 aircraft, and we tried to and this table, one of these tables shows the the values of the aircraft or the propeller RPM, as well as the aircraft Mach number, and as well as a typical thrust requirement for the ATR 42 case at the takeoff condition. So, so this is the one of subroutine what we have developed, which estimates not only the blade solidity as well as the angle of attack distribution, as well as, or you can say the lift or drag distribution along the blade span for a particular thrust requirement and fixed blade solidity. So what it does is like you can see the red path over here is a subroutine for estimating the blade solidity, where user can input a desired chord distribution of the chord along the blade span and the desired lift distribution. So it rescales accordingly the solidity, that is the blade chord, to match the required thrust. So once we know the blade solidity and the required thrust, the user can provide a kind of airfoil type, maybe symmetric or cambered airfoil. You can provide a kind of anything like, but for just a kind of example, I have provided 3 different types of airfoil. One is like symmetric NACA airfoil, and another 2 are cambered airfoils, that is NACA 4312 and NACA 6312, where user can provide a desired now the chord distribution, lift distribution, as well as the airfoil type and the blade solidity and the thrust requirement, and then This subroutine is just changes local angle of attack, that is a local incidence on the blade, and to require to to maintain the thrust distribution and the overall thrust distribution as the same. So you can see that one of the results shown over here in the left hand side figure. I've shown it for three different airfoils. One is symmetric and two cambered airfoils, and we can see that we are able to achieve a kind of a similar thrust distribution with this subroutine, but obviously the angle of attack or the local incident distribution is slightly different for different airfoil, which makes sense. So to do the theoretical calculations, we use the different means to show our overall results. We use the different noise matrices, that is the overall sound pressure level, and and the next one is a PWL, which we call as a kind of integrated number over the emission angles, ranging from 10 degrees to 170 degrees at bottom of the propeller. So which is a kind of emission angle we say. So we again estimate the overall sound power level, that is the quantity, which is a kind of integrated number over the frequency as well as the emission angles over the bottom hemisphere, and which is very helpful to look at the balance between the tones and the broadbands, and I will explain you a bit in a moment. So the frequency range we consider is from 50 to 12.5 kilohertz in a 1/3 octave band. And as I mentioned, the emission angles we take from 10 to 170 degrees. So this is the one of PWL graph, which shows the spectral characteristics or the spectral balance between the tones and the broadbands. And we can see that the tones are kind of restricted towards the low frequency, and at the high frequency the broadband noise has been dominated. So I just showed four graphs for the four extreme blade number and tip speeds, and what we observed is that there is a reduction in the tonal noise with increase in the blade number due to the reduction in the radiation efficiency, which I will show in a moment how we can connect it to it. And for a fixed blade number, we saw that there is increase in the tonal noise uh, at high MT, because it has a both contribution from the source strength as well as the radiation efficiency. And the one of the major important finding is that even though the tonal noise is varying much with blade number and the tip speed, the broadband noise is a kind of almost more or less has a flat response, or it is more or less is flat. So to explain this balance between tones and the broadband spectral characteristics, what we did is we tried to look at the modal source breakdown for the tones as well as the broadband. And we can say the main differences in the behavior and the character of the tonal and broadband spectra and directivities are due to the number of acoustic modes that can be excited. So to look at, we are plotted a kind of modal source breakdown with respect to uh, kind of mode order new, which is kind of discrete for the blade passing frequencies, and but for the tones and for the broadband, it is a kind of integer in nature. So one of the left hand side figure, I shown a kind of modal source breakdown for a odd number of blades going from 1, 3, 5 to 7 at in the around the frequency range of 100 hertz, 350, 500, and 800 hertz. And we have plotted a similar kind of plotted a broadband noise in a similar frequency range, and we can see that for each individual frequency there are a number of acoustic modes that contributes for the broadband noise. That means the broadband noise has been distributed over a wide range of frequency range. And you can see that as you increase the frequency, the number of modes that contributes to the particular number of modes that contributes to the overall broadband noise has been goes on increasing. So that shows that even though we are increasing the frequency, the number of modes that contributes to the overall broadband noise is been increasing, and they are having a different radiation efficiencies. That means the broadband noise won't drop drastically with increasing the frequency. Okay, so, but the tonal noise seems to drop drastically with increasing frequency, which makes sense. And again, in the right hand side figure, we had plotted like in a non-dimensional form, and we saw that we can see that the all like broadband model distribution is collapses very nicely. So this behavior also can be can be helped to explain the directivity terms, where I have the bottom figure I have plotted OSPL with a range of polar angles going from 10 degrees to 170 degrees, and obviously we can see that the tonal noise it peaks around the plane of rotation, which is close to 90 degrees, while the broadband noise is a minimum near the plane of rotations because as you go away from the plane of rotation, the number of modes that contributes to the broadband noise are increasing. So as we saw, like we saw the spectral characteristics as well as the directivities, but in order to see how the where the tones has been dominated and the broadband noise has been dominated with respect to the change in the blade number and tip speed, what we have looked at is like we looked at overall sound power level, which is a kind of, I already mentioned that it's an integrated number over the frequency as well as the space. So I have shown overall sound power level in a kind of 2D matrix where the x-axis shows the number of blades and y-axis shows a kind of tip speed going from 0.40 to 0.77. So the each individual element shows a particular combination of the blade number and tip speed. And what we saw is like the tonal noise is dominated at the low blade numbers as well as the high tip speed, which makes sense where they're like the radiation efficiency of the tonal noise is very high as well as the source strength is also contributing to it. But at the broadband noise has been dominated at the high blade numbers and the low tip speeds where the tonal noise is very minimum. So we can see even though there is a low radiation efficiency, the broadband noise has been dominated at the high blade number as well and a low tip speeds. So to look at into more detail, I have just taken a kind of vertical sections of this 2D graph, and I've shown you here in the bottom figure, where you can see that with increase in the blade number, the tonal noise has been reduced drastically, but the broadband noise is not changing much with respect to the change in the blade number as well as the tip speed. This is because as we are increasing the blade number, we are reducing the chord. Okay, and when we are reducing the chord means the boundary layer thickness is becoming thinner and thinner at trailing edge of the blade, which compensate the source strength, which reduces the source strength of the broadband noise. That means we can see that we can say that the increase in the blade number has been compensated by reduction in the chord for the broadband noise. So the broadband noise is like kind of remains more or less same for the change in the blade numbers. So like we talked everything about now predicting all the tones as well as the broadband noise, but we did a kind of quick experiment to see or to see how the qualitatively our tones and the broadband balance look like with respect to our major results. So for that we did a kind of anechoic chamber measurements with different number of blades, and I shown is a kind of 5-bladed propeller over here, and the microphone arrangements which goes from 1 to 5 microphones in a quadrangle. So we changed the blade numbers from the 2 to 7 blades, and the left hand side figure shows kind of major results and the balance between the tones and the broadband, and we can see there is a kind of shift between the tones and broadband at around blade number 4 to 5, and the similar kind of stuff we observed in our predicted results. And but we this the black line was showing like kind of contributions from all other tones, like not only the fundamental but like higher order tones as well. But when I try to look for just a first blade passing frequency, we can see that the shift has been slightly, the balance has been slightly changed, and which we can obviously say that there are higher order tones which also contributes to the overall tonal noise. But the one thing I would like to mention that the measured amplitudes, like for the difference between the measured amplitudes and the predicted amplitudes, it's quite high at the high blade numbers due to the inflow distortion coming onto the blades, which again contaminates our measurements. But this gives a kind of qualitative validation for our predictions. So apart from that, we also looked at the effect of the airfoil geometry, and what we observed is like, and I have shown the three different 2D plots as previously, but for the different airfoil shapes. One is for the symmetric NACA 12 and another two for the cambered airfoil. And what we observed is like the predicted tonal noise are almost identical, but the broadband noise predictions are slightly different, owing to the variation of boundary layer thickness at the trailing edge. And I just shown like kind of variation in the broadband noise for the four-bladed and eight-bladed for symmetric and cambered airfoil, and we can see that the broadband noise is always higher for symmetric airfoils, which makes sense because we are performing this study at a constant thrust, and to produce a similar thrust or the similar lift, uh, the symmetric airfoil has to be at higher angle of attack or at higher pitch, which increases the boundary layer thickness at the trailing edge, and ultimately it increases the source strength or the broadband source strength. So until now, we looked at the uninstalled propeller noise. Now we will look at the installed propeller noise, which is upstream of the wing, and we'll look at the balance between the rotor alone and various interaction noise sources over a range of blade number and tip speed. So these are the results we already published in one of our AIAA conference in 2022, which was held in Southampton itself. So at any point, if you have any questions, you can type in a Q&A session or the Q&A chat box. I will try to take them after the presentation. So this shows like this one of the figure over here shows a typical propeller mounted upstream of the wing, and you can see there are various noise sources associated with it, but they can briefly or they can briefly kind of categorize in terms of rotor alone as well as the interaction noise sources. So we have various interaction noise sources like wake interaction noise source, that is wakes of the propeller going and interacting with the downstream wing. We have the bound potential field of the wing where the rotor is interacting with it, or we have the potential field of the rotor which is interacting with the wing, as well as we have the rotor wake turbulence interaction, we have the tip vortex interaction. There are numerous sources associated with it, but the right hand side figure I have just tried to classify them in terms of the rotor alone as well as interaction noise source. So for the rotor alone, we consider the tones, as I already explained, as a loading as well as thickness noise, and we for the broadband we consider the self noise. But for the interaction, we consider the tone noise as a kind of viscous wake interaction, potential field interaction, as well as the tip vortex interaction. And for the broadband, we consider the wake interaction. So we know that there are numerous sources associated with it, and like we want to look for how this noise sources changes with respect to change in the blade number and tip speed. So for that, we again fix our constraint. For the propeller, as usually, we are like fixing the blade solidity as well as the thrust. And what we assume for the wing is like there is an ideal lift distribution, and the maximum weight at the takeoff is balanced by the lift force generated by the wing. So we assume a kind of idealistic wing, and we again change the blade number and the tip speed on the propeller, and we change the separation distance between the propeller as well as the wing, and we check like how the individual noise source mechanism emerge as a kind of dominant source mechanism. So uh, there are like various types of formulations, as we have said, but like we are trying to use counter-rotating propeller theory, where we assume that the second row as a kind of two-bladed with a zero rotational speed. And why we use this theory is because we try to look at various literatures, and what we realize is that we already have a well-established counter-rotating propeller theory, which is well validated with the experiments as well, and that can be used to estimate noise associated with the propeller wing configuration. So for the tonal interaction noise sources, as mentioned by T1, over here, we use the Paris model, which assumes that for rotor alone, obviously we assume as a steady load in a blade frame of reference, and we assume a kind of isolated blades, and obviously we take as a kind of flat plate response for interaction noise as well as rotor alone noise. For the tip vertex interaction, we use a kind of one of the formulation proposed by the Kingan and Selp, which uses a kind of Mazigi type model, and where the tip vertex source strength or the kind of velocity distribution due to the tip vertex can be expressed as a kind of monopoles and dipoles, which are placed along the helical tip vertex. And obviously we again use a kind of isolated blades. There are like kind of various underlying assumptions or the mathematical theory behind it, and you can find it in one of our publication, but I don't want to explain it over here, but I just try to drag the one of two major assumptions or the background behind these formulations. Broadband noise, we obviously use the Blandu's theory, where we use the strip theory for the isolated blades, and also we assume the isolated blades that there is no interaction between the blade to blade. And the pressure spectrum model for the self noise, we use the Rosenberg model, and we use the X point to estimate the boundary layer parameters, and obviously we use the flat plate theory. So again, as similar to the kind of tones and broadbands we I explained in the previous slide, I have tried to show similarities between these two formulations. Again, these two formulations have kind of source strength as well as the associated radiation terms to it. And all the entire tonal formulation can be collapsed into this kind of generalized formulation, where I is a kind of integral which has a source term as well as the radiation term, which is expressed in terms of the Bessel functions. And for individual source mechanism, either it is a kind of rotor alone or the interaction noise source, the source strength, which is represented by a green S of R over here, is changes. That means just the source strength changes, but the entire formulation is a kind of pretty much similar. And the same over here for the broadband noise, we already saw here. There are contribution from the various different modes for the rotor self noise. But again, if you look for the broadband interaction noise, again we have the three summations, which comes from the two rotors as well as the one of the azimuthal mode, that is a Q of the turbulence. So we made a kind of simplified assumptions where we assume that our the propeller wing configuration is a kind of simplified configuration where we don't have sweep in the propeller wing as well as the uh, propeller as well as the wing. That means the wing can be modeled as a kind of rectangular flat plate behind a propeller, and we don't have a lean or offset. That means the axis of rotation of the propeller exactly passes through the wing. That is, there is no offset between the wing and the propeller. So this makes our life easy, and we can easily use the theory of counteracting propellers. And obviously, as I shown before, we tried to look at the overall sound power level, that is OSWL, and again plotted on the 2D plot over here over the range of blade number and the tip speed. And as this is the plot for the rotor alone noise, and we can see that as I explained already, there's a tonal noise which dominates at the low blade number and high tip speed, and the broadband noise has been dominated at the high blade number and low tip speed. So these results are slightly different than what I shown previously, because these results are produced by a slightly different call distribution than the previous. So we assume a kind of baseline case which has a separation distance between the propeller and the wing is of 0.72, and this separation distance is from the mid chord of the propeller to the mid chord of the wing, and which is close to 0.72 for a baseline ATR42 configuration. So when you add a wing, what is happens is like the broadband noise, which was dominated at the high blade number and low tip speed, has been taken over by the interaction noise source, and the rotoral noise has been restricted towards the extreme high blade number and extreme tip speeds, which makes sense now because now this entire region has been taken over by the interaction noises, which is mostly tonal in nature, which I will explain a bit in a minute. So in terms of the wing effect, we can consider, if you try to take as a kind of delta OSWL, we can see that the wing is mostly affecting at the high blade number and the low tip speed. So this wing is mostly affecting in the tones, and which is combination of wakes and the potential field. That means the tonal wake and the potential field emerges as a dominant noise source mechanism at high blade number and tip speeds. So one can say that, like, just if you're looking for the isolated propeller, one can say that the configuration will be quieter at the higher blade number and low tip speed, but it may not be the case when you mount rotor close to a wing. So to look at more details, I just tried to show the rotor alone as well as the interaction noise sources for one of the blade number. There's a 12 blade number and the separation distance of 0.72. Here you can see that as we mentioned earlier, the rotor alone dominates at the high tip speeds, but at the low tip speeds, the broadband noise dominates. But when you install it very close to the wing, the interaction noise takes over at the low tip speeds. And what happens is, like, there is a balance between the interaction as well as the rotor alone noise source somewhere here, which gives a kind of low noise configuration. Okay, but this balance between the rotor alone and rotor alone and the interaction noise source strongly depend on the number of blades as well as the separation distance. If you change the number of blades and change the separation distance, this balance between the rotor alone and the interaction noise source shifts towards either low tip speed or either at high tip speeds. So so when you try to look for which interaction noise source dominates over here, we looked at individual noise source mechanisms, and what we found out that this region has been dominated by the tonal wake interaction noise source, and this high region over here, you can see over here, is dominated by the forward potential field, which makes sense because at these low tip speeds, the propeller has to generate a similar kind of thrust. So to generate the similar thrust, we need to generate, excuse me, one need to generate a higher lift and lift coefficient, you can say, or the higher lift. For that, the propeller are running at higher pitch, which increases the drag coefficient, which increases the drag on the propeller. And we know that the tonal viscous source strength is proportional to the drag coefficient from the propeller, and which increases overall wake interaction noise source. So that's why the wake interaction noise source increases as you reduce the tip speed. But when you're trying to increase the speed of the propeller, the pitch of the propeller goes down to maintain the thrust, and the wake interaction noise source goes down over here. But at the high speed, what happens, there is a kind of big wing behind it, behind the propeller, and it has a very strong bound potential field. And when the propeller runs at very fast speed, it runs that potential, it cuts that potential field very fast, and the overall unsteady noise on the propeller is increases due to that potential field. So that's how at high tip speed the potential field is a kind of dominant interaction noise source, but this in this region already the rotor alone dominates for a particular configuration of blade number. But if you change the blade numbers, it may happen that the rotor alone noise goes down and the potential field may be a dominant noise source mechanism. So Apart from that, again, we tried to look at the effect of separation distance between the propeller and the wing, and we took a kind of idealistic separation distance, which is like a Z by D of 0.35, where you can see the dt is the diameter of the propeller, and the Z is a separation distance between the wing and the the propeller. So when you are like very close to a wing, the entire test matrix has been dominated by the interaction noise source, but when you're increasing the distance between the propeller and wing, the interaction noise sources are reducing, and which makes sense. And when you go to the high separation distance between the propeller and the wing, again the rotor noise becomes a kind of a dominant noise source at a low blade number and high tip speed, and the interaction noise has been restricted towards the high blade number and low speed. So until now, what we looked at is a kind of axisymmetric field. That means we didn't look at the directivity as such, but we want to look. But when you look at the directivity of one of the wake interaction noise source, because over here we can see the wake interaction noises is one of the dominant noise source of mechanism, which we needs and which needs a more attention over here. So for that, we try to look at the directivity of wake interaction noise source in an azimuthal direction for even and odd blade numbers, that means blade number of 6 and blade number of 7. And we try to add the phase of each mode. And what we realize is that for even combination of M into B, there's M is a kind of harmonic index and a B is a number of blade of the propeller. The unsteady blade response on the two sides of the wing due to mean wake interaction are in antiphase, leading to a kind of zero pressure below, that is like exactly below the wing. That means when the propeller is rotating over here, there is a downstroke at this side, and similarly matching upstroke is on that side. So the two kind of acoustic fields are antisymmetric, and they cancel each other exactly below the propeller. Okay, so you'll get null, kind of null or zero wake interaction noise at exactly below the propeller, which may be a point of certification for these kind of aircrafts. But what happens is like but in reality, this may be taken over by the other interaction, other sources like a broadband noise, and we may not get a null, but we may get a kind of lower interaction noise source just exactly below the propeller wing configuration, which is a kind of gives a kind of rough design guideline, where if one has to put a kind of even combination of blade number and like M into B to have a kind of less interaction noise at the point of certification. So until now, what we saw is like just a kind of simplified propeller wing configuration with no sweep, lean, and offset. And what we saw is a kind of the wake interaction noise source is one of the dominant interaction noise source at the low tip speeds. And to the and a kind of we will have decided to look at more into it. And what we did is like we tried to incorporate a more realistic wing, which have a kind of wing sweep, lean, and offset. And we saw a kind of how we can take advantage of obviously, like if you see these wing sweep and lean and offset are like comes from the kind of structural or aerodynamic requirements, but we can make use of these realistic wing features to design a low noise propeller wing configuration. And this is like these results we already published in one of our AIAA conference, is 2023. So So what is exactly mean by wing sweep, lean, and offset? I shown over here. That means I shown a definition of those all three parameters. The first one shows the wing offset, where the propeller axis has a kind of offset with the wing, so which is defined over here by H. And the wing may have a sweep. That means the wing might have swept back compared to the uh, propeller plane of rotation, which is shown over here when you look from the above. And again, wing may have a lean, which will, when you look from the front, and this can be represented by a lean angle, which is capital phi. So we quickly formulated one of propeller wake interaction uh, formulation with the realistic wing sweep, lean, and offset, where we assume a kind of already defined propeller wakes, like let's say the slislin wake profile. And what we do is like we transfer all these wakes to the downstream of the wing, and we try to estimate the upwash on the wing surface. And from there, like we use a kind of a wing response function, which is simplified one, which covers both low frequency as well as the high frequency region. And we use obviously the semi-infinite flat plate theory, and those dipole sources again we extrapolate to the far field. So just a quick recap, like this polar angle is like kind of the angle which is goes below the below the propeller, and the azimuthal angle is a kind of the angle which goes in the plane of rotation of the propeller. So to look at the quick verification of our new proposed theory, we are try to compare our predictions for the simplified propeller wing configuration with the no sweep, lean, and offset, and we compared with the counter rotating propeller theory. And what we observed the same directivities and amplitude for the both predictions, but the propeller wing configuration is much faster and like much simpler, because all the response function are simply in terms of the sine and cos, and we don't need to add number of modes as we do with the counter rotating propeller theory. Again, we looked at the effect of lean at constant at zero sweep and zero offset, and what we saw is like I have plotted just like the wake interaction noise for the first two harmonics at 45 degree of azimuthal angle, 45 degree of azimuthal angle for a baseline configuration, that is with a blade number of 6 and the tip speed of 0.62. So where we can see that the wing lean has no effect on the interaction noise other than rotating its directivity by an amount equal to an lean angle, because which makes sense when you give a lean angle to the wing. Again, it has to be a kind of a null position somewhere over here at the 45 degrees, which can be seen over here. So in conclusion, the wing lean has a kind of minimal effect on the overall uh, amplitude, but directivity wise, yes, it changes the directivity. But when you try to look at the wing sweep, okay, for a constant for a zero lean and a zero offset, we can see that when you increase the sweep angle, like the sound pressure level, the interaction sound pressure level slowly increases, which can be related to the kind of having a sonic point interaction or sonic point along the wing leading edge, and when there is a kind of no sonic point along the wing leading edge, a kind of there is a drop in the interaction noise source. I will explain a bit in a moment what is meant by sonic point along the wing leading edge. But again, we saw a kind of similar kind of behavior for the wing offset as well, where we saw a kind of the noise interaction noise source is almost the same kind of, it tried to maintain until some offset value, and then it drastically reduces, which can be related again to the sonic existence of sonic point. So what we did is like we saw like wing sweep and offset has a kind of major impact on the interaction noise source. So we are trying to look at the results for over the range of sweep angle as well as sweep angle and the offset values. So we changed the offset from 0 to 30 degree and sweep from 0 to 30 degree and offset from 0 to 1. 0 represents that exactly the simplified kind of case where the propeller and the wing has no offset. But when it's offset as 1 means like it's the propeller, the wakes of the propeller is just missed by the wing. Okay, so again, this is a kind of, we have plotted OSWL, like integrated number over the kind of space as well as the frequency. And what we saw is like the high noise region has been restricted towards the low sweep and as well as low offset. But with the kind of slight combination of offset as well as the sweep, you can enter in a kind of low noise a kind of low noise configuration where you can design your configuration with a particular combination of sweep and offset, where you will get a lower interaction, wake interaction noise source. So this wake interaction noise source can be related to a kind of trace tip Mach number along the wing leading edge. Means like when the rotor is rotating, there is a kind of interaction point which goes along the wing leading edge. When the velocity of that trace point becomes a kind of subsonic, you will get a lower noise configuration. So we again try to look at the rotation effects of the propeller. So let's see, like we saw a kind of port side propeller over here where the rotor is rotating in a kind of clockwise direction. When you saw from this side, or when you saw from the front, it's rotating in a clockwise direction. But when you have a kind of another side, when you have a propeller wing configuration on another side of the engine, but they are rotating in a kind of same direction, which is called a starboard propeller, then it sees a kind of a negative sweep on it, because the sweep angle has been now the negative, which can be seen as a kind of replica of this port side propeller with a kind of negative offset. So we have just plotted a kind of a negative offset, or we have just looked at the negative offset cases with the positive sweep, just to show a kind of how this configuration, how this negative offset or the rotation makes a big impact on the overall noise. So this first bit part is as usual what I have shown in the previous one, where the high noise region has been restricted towards the low sweep and low offset, and with the slight increase in the sweep angle or offset, you can get a kind of a low noise, we can directly reach into the low noise region. But when you have a kind of negative offset or the same or the negative sweep, what is happens is, like, even though if you increase the sweep as well as the offset, you won't be able to reach a low noise region very easily. So it's better to have a kind of propeller which has a kind of positive sweep or the positive offset, or the propeller which is rotating on other side for the other side of the aircraft. So in summary, like if you look for the isolated propeller, like we have seen that the tonal noise dominates at the high speed and the low blade numbers, and the broadband noise dominates at the high blade numbers and the low tip speeds. And the main difference in the behavior and the character of the tonal and broadband spectra and the directivities are due to the number of acoustic modes that can be excited. And when you again look for an install propeller, when you have the propeller installed upstream of the wing, and we use the theory of control-rotating propeller, what we saw is, like, addition of the wing near to the propeller change the physics of the noise generation, and as a result, various interaction noise sources emerge as a dominant mechanism of noise generation. And the balance between the rotor and as well as the interaction noise source depends on the blade number, as well as the tip speed, as well as the separation distance between the propeller and the wing. And we saw that, like, at low tip Mach numbers, the interaction noise source is a dominant noise source of mechanism, while if you try to go for the higher tip speed with the nominal separation distance, you may find that the rotor alone is a still dominant noise source. And we can able to get a null viscous wake interaction for a simplified propeller wing configuration, which is like one of the takeaway from this talk. And when you look for the installed propeller with the kind of simplified theory, with the including realistic wing features like wing sweep, lean, and offset, we saw that the lean has no effect on the interaction noise generation other than rotating its directivity by an angle amount equal to a lean angle. But the wing sweep and offset has significantly affect the wake interaction noise source, both in terms of amplitude and directivity. And also we have observed a dramatic reduction in the sound pressure levels at higher values of sweep and offset, where the interaction of the propeller wakes along the wing leading edge becomes subcritical, that is subsonic. And the sense of rotation on the propeller related to the direction of sweep and offset is very important and can lead to a far noisier and far quieter configurations. So thank you for your attention, and I'm happy to take any questions. Are there any questions? Yes, there is one question that can this analysis principle be transferable, applicable to wind turbines? Yes, this is applicable to wind turbines as well. Any other questions or suggestions or any thoughts? I can see there is one hand raised by someone. Have you looked at the wing thickness on the resulting noise? Yes, we looked at the wing thickness in perspective of just a wing self noise, but not as a kind of interaction noise source. Yeah, that's the limitation of our theory. We assume as a kind of simply a flat plate. Yeah, there is another question is like, could you comment on tonal and broadband noise components change for the installed propellers with the tip Mach number and the blade type? Okay, so what we observed is like there is a balance between the tones and the broadbands for the uninstalled propellers, but when you install propeller very close to the wing, what happens is the interaction tonal noise sources are the dominant noise sources when you compare with its broadband components. So ultimately it leads to a kind of situation where we are comparing the tonal interaction noise source with the kind of tonal or tonal plus broadband rotor noise source. So the interaction broadband noise source in our case is a kind of very much less, like 10 dB less than the interaction tonal noise source. So, but this situation may change when you have a kind of high flow speed, or like or we have when you have a flow coming onto the uh, propellers, and then again it's interacting with the downstream wing. So we may have an increase in the broadband noise source in those cases. So, okay. So you mean that install propeller with the tip Mach number and the blade okay. What was the question? Could you please comment on how the tonal and broadband non-component changes for the could you please comment on how tonal and broadband components change for the installed propeller with tip Mach number and the blade number? Okay, that's okay. Let me show the results over here. So if you try to look for the install noise source, we have the broadband wake interaction noise source, which goes like very down over here. But we have a kind of tonal wake interaction noise source, which is kind of, let's say, more than 10 dB higher than that. So this is a kind of sitting well below our tonal wake interaction noise source. So we are then just like we are trying to look for just the tonal wake interaction noise source and the rotor noise source. That's the balance between these two for this separation distance. But this balance again, this broadband noise may come up when you have flow into it, or the unsteady flow coming onto the propeller and again hitting back it with the wing. So your broadband noise may go up in those cases. Yes, there is one more question. Are you going to compare further your latest predictions with measurements? Yes, we are going to compare our propeller wing predictions with one of our wind tunnel measurements, and you will see very soon in next or the upcoming AIAA conference as well. Okay, we are about to reach our time. I hope there are no any other questions. If you have any other question, please feel free to reach me. And this is my email ID, and you can find it easily me over on Salford website. So thank you very much, everyone, for your time. And I conclude that this webinar has been completed. And thank you very much for your time. And I think we can stop now the call. Thank you very much. Thank you, everyone.